is in the momentum Adam and helpers basically file, which is this one. So in this code, basically you will see a sigmoid function, you will see a relu function, you will see the initialization for the velocity term, which is for the momentum here. So what basically you do is that if you pass the parameters that you are doing, it defines that number of layers from that parameter, and it loops over those number of layers, and it creates basically delta W and delta B. This is again for the velocity term initialization. So it return your initialized velocity. There's this function which all it does, it basically loads parameters and the gradient. So it basically creates some random parameters and random gradient at first, and basically returns you that. So it's, again, some sort of like initializer. Then we have the initialized parameter functions. It gets the dimensions for the layers, and basically what it does, it creates this dictionary of parameters. That again, that's the same thing that you're using here. It creates this dictionary over the parameters, loops over the layers, and basically creates some random parameter for W and B. Then you have this function to compute cost, which is the same as cost function or loss function. Here is like a binary cross entropy. They have this function for forward pass, and basically it gets the W, all the parameters that we have, and it performs a forward pass using basically NumPy. So here we are in this lab, we are avoiding using the TensorFlow because we were trying to basically to see the details of initializations for this optimization techniques. Then we have the backward pass. And in case you're not familiar with the math of the backward pass, again, just refer to the contents that we have. And we have seen this in the class that the backward pass basically is simply we're using the chain rule concept, and we basically pass the gradient backward in a chain rule fashion. So we have the gradients with respect to the input to the last node or last layer, and then we propagate that backward and calculate the delta W and delta B's across all layers. So that becomes all the our gradients. Then we have this predict function, which gets based on some input and output and the trained parameters, basically it makes the prediction for you. Then we have a function, because so far we just initialized the momentum. So we have this function to basically update the parameters with the momentum. And as we saw in the class, so the way that momentum works is that it first calculates the velocity, which is basically cumulative values of previous velocities from previous timestamps plus basically a scale version of the gradient at the current timestamp. So we have this beta hyperparameter times previous velocity plus 1 minus beta times the current gradient. So you calculate the velocity for delta W and delta B, and then you update W's and B's using the assumption of like basically gradient steps, which is the previous value of W minus learning rate times the velocity that we basically calculated. So that becomes the updates with momentum. Now we have a function, for example, this part of the code is with respect to Adam. So we have a function to initialize the Adam. Basically, it again gets the parameters that we generated here with initialized parameters. Basically, it gets the parameters, and then it basically, what it does, it loops over the parameters, it creates delta WB and delta W, delta W and delta B for both terms that we have in the basically Adam. And we know in Adam we have first momentum and second momentum. So V, or the velocity, is first momentum, and then we have S, which is the second momentum, which comes from the RMS prop. And here basically we need an also function to update the parameters of the Adam, considering if we have this basically parameters, like if you have calculate this first moment and second moment, how could we update the model's parameters with those? So the way that it works, basically, you calculate this moving basically average of the velocity or first momentum, similar function as we saw that in momentum, some beta, which is some hyperparameter, previous momentum from previous timestamps, and plus 1 minus beta times the current gradient. So it's kind of like a moving average. And then we do the same thing basically for the second moment. So here basically we have V and we have V. Actually, sorry, my bad. So this is the corrected bias version. So basically, um, uh, so if you go to momentum, so here after you find the value, you basically compute the bias, basically corrected version of that by dividing the first moment over 1 minus the hyperparameter, the beta that we have to the power of t, which is stand for timestamp. You do the same thing basically for the second moment. That after we find the second moment, we're also going to compute the bias corrected version of that. And then we use those knowledge basically to update our parameters. So this becomes for basically correcting the first moment. Then we have here calculating the second moment basically for delta W and delta B. And what we're basically doing at this point here is that after we have those, we are going to correct those again using the same equation here. And after we have the corrected version for first moment and the second moment for both W's and B's, what we're going to do here is that we're going to update the parameters using basically a gradient descent update. Here, the update term comes from first moment over square root of second moment plus some epsilon to avoid, division by 0. So that's the update parameters for Adam. Then this we have this predict deck. Basically, what it does forward propagation, and if the prediction is greater than 0.5, it returns 1. Otherwise, it basically returns 0, like a true false, like a binary conversion. We have this function that all it does just loads the data, and then we have a function because we wanted to compare Adam, momentum, and gradient descent. And then we have this function that just for gradient descent, which what it does, given parameters and gradients, simply updates the parameters based on the gradient. Then we have this function that basically creates random mini batches, which I'm not going to go over that code. And then we have the model function, which model function, what it does, it basically given input, output, layer dimension, the types of optimizer has parameters like learning rate, mini batch size, beta, beta 1, beta 2, depending on, again, remember beta if it was momentum, beta 1 and beta 2 was for Adam. There's some epsilon and number of epochs, and basically there's another parameter for print cost, which is similar to verbose we saw in TensorFlow. And if the parameter says that the optimizer is gradient descent, there is no initialization, which if it's optimizer is momentum, we initialize using the function that we saw before, initialize velocity. If it's Adam, we use initialize Adam. And then we basically do some forward propagation. We calculate the cost for at every basically epoch for every mini batch. Basically, we do a forward propagation. We calculate the cost. We use the cost basically that we have to backpropagate and calculate the gradients. Then, depending on which optimization basically technique we use, gradient descent or momentum or Adam, we do the update over the parameters using the gradients that we have found. So we already have seen these functions, update parameters with gradient, with momentum, and with Adam. And then we do some print out, and we basically do some plotting. So this is the overall codes that you saw in this momentum lab. So if I go ahead and run this lab, so this is the data that we have. So this is, again, the same code here. So that's the same code again. It just we had it here in order to be part of the Jupyter, but it's the same code that we saw here. So here, this part that we are calling to the model. So we see we create the layer dimensions, start with the gradient descent. So we'll let this to run. And then after that, we're going to do the same thing with momentum. And then we're going to do the same thing with basically Adam. So I'm going to run 3. So as we can see, using gradient descent and certain learning rate, we, after I think it's like a 10 epoch, so we reached to almost 50% basically cost. With momentum, we reached just similar basically value. And let's see for with Adam, and as you can see, with Adam, we reached to much lower basically error or cost. And that's becomes a comparison here. Again, we know that one of the reasons we use technique like Adam is to basically helps us to avoid stocking in oscillatory or flat regions as part of our training by accelerating and trying to get out of those regions. So as it can show that it's basically did a better job in conversions and basically giving us a better model in compared to the other techniques. All right.